Okay, so this is class 3. This is what we have done so far. Okay, we looked at the definition of colloids, motivations to study them, definition of colloidal dispersions, classification, and their stability. Okay, so what we'll do in today's lecture is hopefully two things. One is to look at source of colloidal particles, that is to tell you a little bit about where do they come from, and then followed by that we'll talk a little bit about characterization of colloidal dispersions. I have a long list of things, so I'll try and introduce each of these terms to begin with, and then I'll tell you a little bit about their definition and what are the typical methods that people use for finding these physical and chemical properties of colloids. Okay, and most of the content that I'm going to do is taken from Colson and Richardson's chemical engineering series. Okay, that's the particulate systems and particle technology, chapter 13. Okay. Okay, so any thoughts about the source of, so where do the colloidal particles come from? Okay, the first topic. Okay, so the answer for that would be, it could come from any process, right? There could be an industrial process. You could have maybe things like say size reduction, for example. You have larger particles and you're trying to break them into smaller sizes. In that process, you could get particles which are again in this colloidal length scale, right? You could that could happen through industrial processes. It could also come from vehicular emissions. The lot of stuff that comes out from the vehicles. I give an example of burning of candles, right, in the other lecture. Okay, so it could come from burning of things like that. I can add one more to the list, D. You could have from natural resources, right? Okay, like I was talking about this bacteria, virus, okay, or the latex, rubber latex and things like that, right? So you could also have particles from any source. Okay, but however, as I showed, right, the particles that come when you burn candle, I had shown a picture in which I said that they are, of course, each particle is colloidal size and colloidal length scale, but then they are very complex, right? Okay, the particles that are produced in any of these processes they have a very complex shape and structure. Okay, right? So that is because their formation, okay, that is because their formation occurs in not so well controlled environment. Okay, because when you burn candle, right, so you have oxygen, you have so essentially the environment around the candle burning process is not very well controlled. Okay, there could be fluctuations in temperature and stuff like that, right? That's what leads to the formation of such complex particles of different structure, sizes and shapes and things like that. Okay, so of course there is a lot of interest in studying such particles, right? Because one could be interested in looking, if you look at industrial processes, right, so one could be interested to look at to assess the health hazard, right? So there one could be interested to ask a question as to what will happen if there are fine particles that are produced in an industrial process and then if you inhale them and things like that, right? So each the particles that are produced by each of these processes are important. Okay, there are people who are trying to look at health hazards of such things, people who are trying to look at fate and transport of aerosols, for example. How do these particulate matter that are emitted because of vehicular emission, how do they how are they carried around, how are they present in the environment, stuff like that. And of course people have also used particles that come from these sources, as I was telling, to design what are called as superhydrophobic surfaces and so on and so forth, right? So of course particles from such origin are important. There's interest to look at these systems, but in colloid science, what people are looking at are what are called as model particles. Okay, what I mean by model particles is that these are particles of well defined size, shape and surface properties. Okay, so if you really want to investigate fundamentally a particular phenomena in colloidal science, what you do is you go to these model particles, which essentially are particles of well defined size, shape and surface properties. Okay, so that's the need. Okay, and again, how do you get these particles? Actually, there are a lot of particles that are commercially available. You don't have to worry about buying. You don't have to worry about synthesizing them. They're commercially available. What you're given is an example of 4 different types of particles. A and B. These are actually silica particles. Okay, and if you look at the length scale, they are sub 100 nanometer. So this is about 100 nanometer, right? This is 100 nanometer. So if you look at these particles, they are maybe about 30 nanometer in dimension, and these are about 15 nanometer in dimension. Okay, they are kind of sold in by a commercial name called Ludox particles. You can buy them. They come in liters and liters, not very expensive. And these two are examples of silica particles, SiO2, and this is polystyrene. Okay, and as you can see that they are very homogeneous, uniform, exactly similar size. Okay, so you can buy them and then design experiments to study whatever colloidal phenomena that you would like to. Okay, so that's one source of a model particles which people have been using for several years to study a lot of interesting phenomena in colloids. Of course, you can synthesize them in the lab. Okay, so these are some examples of synthesis from our lab. So these are all synthesized by different people in the lab by well-defined procedures that are available in the literature. Okay, this is not invented by us, so things are already existing. So all that you have to do is follow these procedures and then systematically and in a controlled condition, and you'll be able to produce the particles of that are spherical in shape, that are elliptical in shape, these two, right? So the first set of particles, these are example of again silica particles, which are produced by a technique called Stover synthesis. Stover synthesis. Okay. Again, this is the name of the scientist who found this technique for making these particles. Now, so this particular Stover synthesis, it's a very simple reaction. It will involve water, some ammonia, ethyl alcohol, and a reagent called TEOS, that is tetraethyl orthosilicate. Okay, that is the source of your Si in the particles. Okay, ultimately I'm going to get SiO2 particles. Okay, and just by playing with the concentration of these reagents, I can actually produce particles of very different sizes. Okay, and there's a lot of work that has gone in in the development of this synthesis procedure. It actually involves 2 reactions, a hydrolysis reaction and a condensation reaction. So if you want to more details, you can refer to the literature. But what people have done is they have come up with the correlations that I can use for designing particles of a particular size. So this dP is the size of the particle that I am generating by the Stover synthesis, and I can control that by, so it depends on the concentration of the water that I am using. Okay, that is these two, right? And of course the parameters A and B, which in turn depend on the concentration of the TEOS, ammonia, and a few other things, right? So therefore, if you want a particle of a particular size, what I can do is I can choose my reagents in appropriate proportions and then actually design particles of different sizes. Okay, so that's about Stauber synthesis. These elliptical particles that I was talking, they are obtained by again a very simple technique called force hydrolysis. Okay, again this is a very simple chemical reaction which involves again an iron salt, water, and a few other reagents. Okay, and if you're interested again more, you can read up literature. So I don't want you guys to know the procedure for synthesis, but I just want to tell you that look, there are things available in the literature which you can read up and then follow up and then essentially make model colloids of your choice in the laboratory. Okay, and the last one is by a simple technique which anybody could do in the lab. It's called as nanoprecipitation. Okay, it's a very simple process. Okay, all that it involves is that I take a solution. Okay, and this solution contains it's a solution of a polymer. It could be polystyrene, it could be PMMA or PVA, any polymer. Okay, it doesn't matter. Okay, and that is dissolved in a solvent so that I get a homogeneous solution of this polymer in the solvent. Now what I do is I take this and I add a drop of that into another container which has another solvent, another fluid, which is a non-solvent for the polymer. Okay, so initially the polymer is dissolved in a what is called as a good solvent. That means this is a solvent in which the polymer dissolves completely. I am able to get a homogeneous solution, and I take that solution and add it into a fluid. Okay, and the fluid is a non-solvent for polystyrene. That means this polymer does not like to be in that solvent. Okay, so as soon as you do that, and then if you stir it, you essentially have generation of spherical particles. Okay, that is because the polymer does not want to be in water and it precipitates out, and it precipitates out as spherical particles. Okay, again there is a lot of literature, you can read up a little bit about it. Okay, so what we have done in our lab is to use this polystyrene waste. Okay, this is what is called as EPS, expanded polystyrene, that comes as a packing material, right, for a lot of electronics that you buy. Okay, you can take that and you can dissolve that into solvents such as THF, tetrahydrofuran, acetone, lutidine, doesn't matter, any solvent in which the polymer dissolves, you do that. Okay, you get a homogeneous solution and simply add that to water and you can actually precipitate these particles. Okay, and I can control the of course I can't make particles of single size. As you can see, there are different sizes. Okay, there are ways by which I can control that as well, but I can play with the polymer concentration. Okay, I can play with the amount of water that I'm using for precipitation, and I can play with the mixing speed, right. So what is done here is when I add it, I am mixing it rigorously, right. I can play with the mixing speed, and thereby I can actually control the size of the particle that I'm able to generate. Okay, so this is again some information about the source of particles, where do we get them from, and how do we synthesize in the lab, right. Following that, we will move on to defining or characterizing colloidal dispersion. Okay, so now, the moment I have a colloidal dispersion, okay, that is dispersion of these particles in a fluid, right. Now I may have to worry about several different physical, chemical or physical chemical properties of both the particles as well as the dispersion, right. So if you talk about the particles themselves, okay, one may be interested to know what is the size of the particle, okay, what is its shape, right, and of course the density of the particle is important, it's a useful quantity that you should know for several different things, as we will see little later, okay. Specific surface area, okay, which is essentially defined as the surface area of the particle divided by mass of the particle, right? Right? That is your okay, specific surface area, okay, okay, or if you want to call it as surface area, specific or something like that, okay. So that is the surface area of the particle divided by the mass of the particle, and it typically will have units of meter square per kg or meter square per gram, right, okay. And this quantity is actually useful if people are trying to use colloidal particles for adsorption studies and things like that, right, where the surface area becomes important, okay. So one may also be interested to look at the properties of the dispersion itself, okay. So for example, one may be interested to look at the density of the dispersion, okay. One could also be interested to look at what is called as a volume fraction of particles in the dispersion, right, okay, which is defined as phi. Typically people refer to it as phi, okay, is volume of particles in the dispersion divided by the total volume of the dispersion, right, okay. That's how it is defined, okay. The lower this number is, that means the concentration of particles in your dispersion is smaller, okay, and higher this number is, the concentration of the particles in your dispersion is higher, right. Now, have you heard of this term, grafting density? Somebody's heard of these terms? No, okay. If you look at the images that I showed of these particles, right, okay, these are all solid particles, right, these are all solid particles. In some cases people work with particles which look something like this, okay. This is your solid particle, okay, and on the surface they can put some long chain molecules, okay. These long chain molecules can be put by two different ways. One is by doing a chemical reaction. If I know what is the surface chemistry of the particle, if I know what is the surface of the particle is made up of, I can take a long chain molecule, I can design a reaction so that these chains kind of get attached onto the surface, okay. There are ways of doing that, okay. Or what I can do is I can have a particle, a solid particle, and I can add in some long chain molecules which can physically adsorb. It's not a chemical reaction, okay. However, there's a physical interaction. Maybe you could think about maybe an attraction or something like that, because of which you will invariably have particles which have some molecules on the surface, okay. When you have cases like that, that means when you have a chemical modification of the surface to give chemical grafting, okay, or a physical grafting, which is more because of the adsorption of some molecules on the surface, you can actually define what is called as a grafting density, which essentially is defined as the number of molecules of these number of molecules that you have put on the surface divided by the surface area, okay. Okay, this is number of molecules, okay, maybe per particle. That means if I have a particle, okay, and if I say that, look, I have put in, I don't know, some 10 chains, okay, and if I say that, the particle surface area is, like, say for example, say 100 micrometer square, okay, this is example, then your grafting density is going to be 10 divided by 100 micrometer square, right? So typically this will have units of, some per, uh, micrometer square or meter square or something like that, right? So that's your grafting density. We'll tell you a little bit about why this, chemical grafting or physical adsorption is important as we go along. But at this point, what is important is that there are particles which may have some long chain molecules on the surface, and one would be interested to know what is the number of molecules on the surface of these particles, and that is characterized by a quantity which is what is called as a grafting density. Okay. Now that I've mentioned what is grafting density, you should be able to guess what is surface charge density, right? What do you mean by, any thoughts? Surface charge density. So the surface charge density, as the name itself says, become important if you have particles which have charges, right? I could have a negatively charged particle, or I could have a positively charged particle. Okay, if I know the number of charges on the particle surface, okay, typically surface charge densities will have units of coulomb per meter square, right? And that, so this essentially comes from the total charge on the particle surface. Okay, if I have, like, say 100 like, say charges, for example, say that, I have a particle surface where my surface group is COO minus. Okay, if you have 100 such groups, okay, then the charge that is going to be on the particle surface is going to be 100 times the charge of the electron, right? That's your total charge on the particle surface divided by, again, the surface area of the particle will tell you what is the surface charge density. Okay, so before we talk a little bit about, what is surface charge density, what I'll do is I'll tell you a little bit about the origin of surface charge. So where do this charge on the particle surface come from? Okay, there are different mechanisms that by which the particles can get a charge. One is by what is called as dissociation of charged, or let's say dissociation of surface groups. So what I mean by this is that, see, the synthesis chemistry, right? The people who do colloidal particle synthesis, the chemistry is so advanced that, you can make particles with well-defined charge groups on the surface. What I can do is, if I may ask somebody, they'll be able to give me a polystyrene particle which has COOH groups on the surface. They'll be able to give me polystyrene particles with maybe SO3H group on the surface. Okay. Now, what happens when you have such particles in water? The moment I put such particles in water, what will happen is the groups that you have, it dissociate and it leave out H plus ions in solution. Okay. So therefore, that happens for all the groups that are there on the surface. Ultimately, you will end up with a particle that has a charge. Therefore, the dissociation of surface groups is one of the mechanisms by which the particles can acquire charge. Okay, that's one mechanism. Now, the second mechanism that you can think of, one of the simplest ways is dissociation of surface groups, right? Any other examples that you can think of, or any other means by which the particles can get charged? Polarization. And then you're bringing, was it? It's a polar molecule. Um, you're saying that the particles themselves are made up of something that is polar in nature. Um, See, when we talk about a charge, right, you're talking about the charge on the surface, right? Um, so, I mean, polarization, of course, will lead to, the regions where there's more charge, regions where there are less charge. Okay, typically we talk about something like that when it comes to molecules, right? When it comes to particles, itself, I don't think people think about this polarization as a. Um, so what people can do is there are cases by which um, so this is shifting of electron clouds, right? uh, but there are cases where I can of course polarize the particle, but if I put them in electric field and things like that, you can do that. Okay, but in pure solutions there are other mechanisms by which the particles can acquire charge. Okay, so the second example I'm going to give you is by if I have say particles, right? Now say these are not functionalized particles, they are homogeneously smooth, right? Then what you do is I can add different things to this fluid, right? I have a colloidal dispersion, okay? I can add a charged polymer, okay? Or I can add a charged surfactant, or I could add in some reagents which have some positive or negative ions. Okay, so what happens is in such a case all these things that I've added, okay, they can go and adsorb onto the particle surface. And if I have charged polymer, so a charged polymer I'm going to represent it something like this. It's a long chain molecule, but it may have some surface groups, right, because it's a charged things, it has charges. Therefore, I can invariably end up with a particle that has adsorbed macromolecules, adsorbed polyelectrolytes, which can give rise to charge on the particle. Similarly, I could have a case where I have a particle and the surfactant that I add, it can have a charge groups, either positive, okay, or negative, okay. Thereby the particles can acquire charge because of either the adsorption of polymers, charged polymers, or adsorption of surfactants, or adsorption of charged ions itself. Okay, there could be a physisorption or chemisorption of charges onto the particle surface, okay, and ions onto the particle surface, and that could lead to the charges on the particle surface. Okay, so therefore people think about these four different mechanisms by which the particles can acquire charge, and once you're dealing with charged particles in a fluid, therefore it makes sense to characterize them for surface charge density. Okay, so I have some examples listed here. Again, whatever I wrote up in a schematic form. This is an example where you have a group which is SO3, SO3, OSO3 minus. Okay, that gives a negative charge, and you have a NH2 NH plus group here, right? That gives a positive charge on the particle surface. This is a case where there's adsorption of H plus or OH minus ions, which can make the particle positive or negatively charged, okay, or the surfactant molecules are adsorbed, or the charged polymers that are adsorbed. Okay, so you can think about these different ways by which the particles can acquire a charge. Okay. What can you say about this quantity, surface heterogeneity. Have you thought of this? Surface heterogeneity. Some of the, so she says that some of the surface or the particles, some of the, okay. So she is saying that, look, I have a particle, okay, and she says that some of the surface, you know, may have positive charges, okay, some of the surface may have negative charges, okay. Yeah, so this is an example of a surface heterogeneity, but in this case this is an example of what is called as a surface charge heterogeneity, right? Right. So therefore, surface heterogeneity can be of two types. One is physical surface heterogeneity, or it could be chemical surface heterogeneity. Okay. The physical surface heterogeneity refers to cases where I may not have a perfectly smooth surface. I could have a particle where the things are rough, okay. The surface is not atomically smooth, okay. It has some undulations on the surface, there could be hills and valleys, right, and there is an example where you have a physical heterogeneity. Or you could have a case like this where I have patches on the particle surface where things are positively charged and patches where it is negatively charged. Or you could also have a case where I can have a patch which is hydrophilic, I could have a patch which is hydrophobic, right. These are examples of cases where you can think about chemical heterogeneity, and one also needs to characterize them for this, okay. So this is, you know, the last point is a bit more complex to characterize such things. Of course, there are indications in the literature as to how do we characterize such things, especially the chemical heterogeneity. The physical heterogeneity, the surface roughness, you know how to do it, okay. But however, the chemical heterogeneity is still, you know, something that people are still trying to study, okay. Yeah, go ahead. Yeah, maybe I'll talk a little bit about that maybe in the next class, okay. Yeah, you can think about them as, so what he's trying to talk about is that, look, I can have a particle, okay, where some part of the surface has some chemical, some chemistry, okay, and other part has some other chemistry, okay. Of course, that will come into case where you have a broadly, right, you can say that, you know, this is a particle which has a surface heterogeneity. In this case, it's a chemical heterogeneity, right. So yeah, you can think about particles like that as well. So any questions so far? All these terms, are they clear? The particle size, shape, density, specific surface area, grafting density, charge density, and heterogeneity. Now let's, I won't spend a lot of time on this, but maybe one class or maybe 1.5 class. Okay, so first, characterizing particles for size and shape, okay. So how do we do that? So somebody has given me a colloidal dispersion, okay, and then they'll ask you to find out what is the size of the particle or shape of the particle that you have in the dispersion, okay. What do we do? What is that? She says dynamic light scattering, okay, microscopy techniques. Anything else? Microscopy technique, dynamic light scattering technique. Anything else? Okay, there are also techniques called static light scattering, right? Okay. Again, in microscopy you have optical microscopy, also electron microscopy, right? Again, electron microscopy you have scanning electron microscopy and transmission electron microscopy, right? But what technique that you use for measuring the particle size, okay, uh, depends, and if you have any a priori knowledge about a typical size range that you may have in the dispersion, if you know that, then you can choose one of the technique appropriately. Okay, that means, you know, if the particles are a few microns in size, then I would go for optical microscopy. Okay, if typically dynamic light scattering technique, uh, you know, of course, if you look at the manufacturer specification, they say you can measure sizes from 1 nanometer to about, close to about, okay, 8 to 10 micrometers. Okay, um, and if you look at static light scattering technique, you can measure sizes all the way from 10 nanometer to, a few millimeters itself. Okay, a very large size range. Of course, electron microscopy is, suited, especially transmission electron microscopy is suited when you're looking at particles which are nanometer length scale, right? So we won't go into the details of all these techniques. I just want to mention that there are techniques available in the literature, and you should be able to characterize particles for size as well as shape. Okay. Um, Now, so what you're looking at is a schematic where, what can you say about the schematic? These are particles of, they look of very same size, right? They look like the diameter of each of the particle that you have looks exactly same, right? And of course, you can make such particles in the lab. Okay, and so such particles where the particles are of identical size, they are referred to what is called as mono dispersed particles. Okay, that means, so all these particles are of exactly same size. Okay, but however, I showed you this example of nano precipitation, right? If you looked at the microscopy image carefully, these particles were of different sizes, right? Of course, there are other, examples. So that's this is done by a again a Stover synthesis, which can give very uniform particles like this. However, if your reactions are not controlled, if you're not careful in doing your synthesis, what will happen is you'll end up with the particles like this. Okay, where you have particles of very different sizes. Okay, when you have particles of this kind, okay, such dispersions, you can say that they are what are called as polydisperse. That means you have particles of different sizes that exist in your dispersion. Okay. Now, if you look at the first case, right, monodisperse, if I want to completely characterize, the particles for shape, I can just say that, look, they are spherical particles and then they are of same size, and that's my size. Okay, I can characterize them like that. Okay. However, when you have, polydispersed samples, you talk about what is called as a mean size. Okay, and of course you also talk about what is called as a standard deviation, right? How much does this mean size, okay, deviate, right? So again what people do is you can get microscopy images like this. Okay, there are methods by which I can find out the size of each particles that I have in the sample. Okay, and typically you do that for a large population of particles. 50 not enough, 100 not enough, 1000 not enough. Okay, so when I say that, I just want to go back to these techniques, right? I said that people do dynamic light scattering and static light scattering and these microscopy techniques, right? One of the a very important difference between the light scattering techniques and microscopy techniques is that when you do your size analysis, you are focusing on a very small region of your sample in microscopy. Okay, that means you look at this, right? This is an image from microscopy, right? All you have is, you know, maybe 20-30 particles, right? Of course, I can play with the magnification, I can get large number of particles in this window. However, when you do analysis, people typically limit the number of particles that they analyze to maybe 50, 100, 200, something like that. Okay. However, when you look at light scattering techniques, what happens is that you have a sample, okay, in which there are particles, okay, and you have a beam of light, okay, that falls onto the sample, okay, and then what you do is it basically is when you say a beam of light has some dimension, right? People talk about, you know, 0.1 millimeter beam and things like that. Okay, now people talk about what is called a scattering volume. Okay, so in that volume, even if I take a very dilute dispersion, like say 0.001 percentage particles, the number of particles that you're going to have is, if you say like say silica particles of 50 nanometer diameters, okay, you can roughly calculate and show that the number of particles could be of the order of 10 power 15 or 10 power 13, some numbers like that. That means, so the number of the size that you obtain by light scattering, it is an average of a large number of size that, you know, the scattering that occurs because of a large number of particles that are in that volume. Okay, therefore, the sizes that one report from light scattering technique are more representative of the sample that you're dealing with than the techniques in which you use microscopy. Okay, so that's okay. So we'll come back to that. Now, if you have a way of, you know, finding out the size of the particles, then maybe I'll just stop here. Okay, so I think just about time. So I'll just stop here. So what we'll do is we'll continue with the characterization in the next class. Hopefully, I'll try and finish up the characterization by the next lecture itself. Yeah, cool. Thanks.